Hi, I'm Michael Pfeiffer from Industrial Metallurgists. In this brief video, I'll talk about metal fatigue. Here are the topics I'll be covering in this video. First, I'll talk about the definition for fatigue, the requirements for fatigue to occur, the three stages of fatigue failure, fatigue fracture appearance, and finally, factors that influence fatigue life. And the picture here shows a shaft that fractured during use due to fatigue. So fatigue is the localized permanent damage to metals that are exposed to a cyclic stress. So cyclic stress is a stress that cycles between a high and a low stress repeatedly. Localized means that the damage is confined to a portion of a component or joint. So in the shaft that fractured here, we see that there's damage only to one portion of the shaft. The stress can be uniaxial, bending, or torsional. We'll discuss in a later slide. Some portion of the stress has to be tensile in nature. So there must be a tensile stress in order for fatigue to occur. There are a variety of sources. Can be the source of the stress. It can be applied force, vibration, acceleration, and deceleration. All can be forces that can lead to the formation and growth of a fatigue crack. There are three requirements for fatigue to occur. First, there has to be a cyclic stress. The stress must have at least a tensile component to it. So we can have fatigue due to tension, shear, as long as there's some part of that stress is tensile in nature, bending, and torsion. And finally, the local stress must exceed the metal's yield strength. So what's important to understand about fatigue is that we have formation of a crack at a stress that's less than the metal's nominal yield strength. And what happens is that at the localized area, what we see is that actually the stress on the metal, this localized area, exceeds the metal's yield strength, but the stress that's on the entire piece of metal does not exceed the metal's yield strength. So the stress is exceeding the yield strength at a localized spot in the metal. But we don't see any deformation of the metal because the overall stress on the metal is less than the nominal yield strength of the metal. There are three stages of fatigue failure. The first is crack initiation. During this time, microcracks first form at the surface of the metal, and then the microcracks grow and coalesce to form larger cracks. After that, the next stage is crack growth, when the crack grows with each stress cycle. And finally, there's fracture. Fracture occurs when the cross-section of intact material is too small to support the applied load. So crack initiation takes some time. For some metals, it can be, the time it takes depends on the metal, on the strength of the metal. For some metals, it can be below 1 million cycles. For others, it can be above 1 million or above 10 million cycles. So it just depends on the metal and how strong the metal is. This shows the fracture surface appearance. First, it's a diagram, and then of an actual part that fractured due to fatigue. So this is a diagram of a fracture surface, and what we see is a crack origin. See growth of the crack, and then the part that's failed due to overload. Sometimes we can see features on the surface that's failed due to fatigue that indicates the origin of the crack, and it helps us understand that fatigue occurred. These are called beachmarks, and these are sometimes visible with the naked eye. So what happens is the crack forms and it grows, and then finally, when the remaining intact material doesn't have enough strength, then the remaining intact material will fracture. Sometimes we can have a large portion of the part that fractures due to overload, and sometimes we can have a small portion of the part that fractures due to overload. It just depends on the total applied stress to the metal, and also on the strength of the metal. And this shows a shaft that fractured during use. The crack started here and moved across the surface, and then finally this is the part that failed due to overload. So this part failed under bending fatigue loads. There are a number of factors that influence the fatigue life of a component. First, there are mechanical design features that are stress concentrators. Laser marks, notches, changes in or abrupt changes in cross section. These act as stress concentrators. Stress concentrators are features on a component that concentrate the stress that results in the local stress being higher than the nominal stress on the metal. So with notches and laser and marks and abrupt changes in cross section, we see that the stress at these locations is higher than the stress over the cross section of the material. The alloy strength also influences it. So for steels, as the strength gets higher, the number of cycles to failures increases, or the load that can be tolerated for a certain number of cycles to failures increases. Non-metallic inclusions and manufacturing defects are also things that can occur inside of the metals that are also act as stress concentrators and result in the localized stress being higher than the nominal stress on the material. So inclusions in metals and manufacturing defects localize the stress within the metal. So in steels, non-metallic inclusions include manganese sulfide inclusions or aluminum oxide particles or titanium nitride particles. And manufacturing defects might be laps, seams, and voids in a material. Surface residual stress can reduce fatigue life or improve fatigue life. So if you have residual stress that's tensile in nature, then that will add to the applied stress and will result in a reduction in the fatigue life of a material. Whereas having a surface residual stress that is compressive in nature will subtract from the applied tensile stress and help improve the fatigue life of a material. And there are things that we can do to a metal to reduce the tensile stresses at the surface or make it so the stresses at the surface are compressive in nature. Surface roughness will impact fatigue life because they can again be any roughness in the surface of a material can act as a stress concentrator. So grinding marks, machining marks, anything that adds to the surface roughness will reduce the fatigue life of a material because the surface roughness will enable cracks to form at the surface or enable faster formation of cracks at the surface. So making a part smoother will help to improve its fatigue life. And finally, the metal's fracture toughness. Fracture toughness is related, indicates the size crack that a material can have in it before the material fractures catastrophically. So as a fatigue crack is growing through a metal, the higher the fracture toughness of the material, that material can then withstand a larger crack before it fails due to overload. Whereas a material that has low fracture toughness or poor fracture toughness can only withstand a small crack before the rest of the material fails due to overload. So that's it for explaining about fatigue and how the requirements for fatigue to occur, the steps of the stages of fatigue cracking, and the factors that influence fatigue life. If you'd like to learn more, we have a video that's a recording of a previous webinar. It's called Preventing Metal Fatigue. It's a half-hour-long video, and you can access it at this link. Also, we offer design and failure analysis help, for engineering help, for designing components, for improved fatigue life. We have information here at this link. And then if you need help with failure analysis of a component that you think failed due to fatigue, then you can go to this link and you can contact us by clicking on the Contact Us button. So that's it. If you have any questions or comments, feel free to email or call. Thanks for watching, and good luck with your metals. Bye.